In a related problem, similar to the one that we just did, says calculate delta S for the following reaction. It's given a little table this time, much smaller. And then we're going to do delta H and delta G as well. So similar to what we've done before. Let me fill this in. NO2, 240.1. Jump in any time if I mess this up, by the way. 304.3. So it's going to be products minus reactants times coefficients. So 304.3 minus 2 times 240.1. I get minus 175.9 joules per mole Kelvin. That's negative. We're not surprised by that because we're going from 2 moles of gas to 1. Let's do the same thing for the other two thermodynamic functions, delta H. Yep, double check everything. 9.2 minus 33.2 times 2 minus 57.2. This time in kilojoules per mole. Good. I wrote out all my units in my problem so far. Do delta G. And my delta G naught reaction, my change in free energy of reaction under standard state conditions. 97.9 minus 51.3 times 2 minus 4.7. All right. So we could say tends to be non-spontaneous, tends to be spontaneous, under standard conditions is spontaneous. Always good to think what these calculations mean. And then we get to calculate K. Well, here's where we relate thermodynamics to equilibrium constant. It's going to be delta G naught reaction equals minus RT ln K. And this is an equation that's on your conversion and equation sheets, which you should have handy when you take your exam and when you do your homework. And it says, because both reactants and products are gases, it is a Kp. If our reactants and products were aqueous phase, then it would be a Kc. And if it was some aqueous phases and some gas phases, then it would be an amalgam, a mixture. It would be somewhere between a Kp and a Kc. But don't worry, on your exam, they'll all be either Kps or Kcs. We won't mix it up like that. Now, you've been asked for K, Kp in this case. So I'm going to rearrange this equation to solve for Kp. I'm going to divide both sides by minus RT and move my ln of Kp over to the left. And then I will exponentiate both sides. And Kp equals E to the minus delta G reaction over RT. My delta G reaction is minus 4.7 kilojoules. I put everything in joules. That's minus 4,700 joules per mole divided by RT, where this is not the ideal gas law, so we have to use the 8.314. Joules per mole Kelvin. We also see that the joules will cancel here, so that's our other hint. And T, oh, we're at standard conditions, so our T has to be 298 Kelvin. And if we multiply all this out, we have, let's see, 4,700 minus divided by 8.314 divided by 298. Oh, I think I ended up with double negatives here. Yes, that's exactly what I'm supposed to be, because there's a negative in the equation and there's a negative in my delta G. So I will change that to a positive, and I will hit exponential, which is shift, this button right here, 6.67 equals Kp. And now I'm thinking, I hope I got my double negative in there when you do this or a similar problem on the homework. If not, let me know. Any questions so far? Okay. We see that K is a little larger than 1, which means this is slightly product favored, though not, I wouldn't consider it really product favored. Now, keep going with this. It says, based on your previous calculations, calculate QP, and it should say the reaction quotient. Because that's what QP is. For the following reaction, and where now we have partial pressures. So QP is going to be the partial pressure of our product over the partial pressure of our reactant raised to the coefficient. And what you're noticing is that thermodynamics does interface with equilibrium constants rather nicely. Plugging in my equilibrium pressures here, or sorry, not my equilibrium, just my random pressures. 0.050 over 1.0 squared. I just get 0.05. And Q's and K's are unitless, even if it looks like they should have units. And it says, based on your previous calculations, calculate QP, and based on your values for Kp and Qp, is the reaction spontaneous under these conditions, which are the same in this question? And Qp is less than Kp, which means that the reaction will shift right, which is the forward direction. To get to equilibrium. Which means, since the reaction is shifting to the right, the reaction is spontaneous, yes, in the forward direction. And here on this problem in particular is where we look at how does equilibrium talk about spontaneity. So equilibrium says the reaction will shift right. So here, equilibrium versus thermodynamics. Where thermodynamics says the reaction is spontaneous, in forward direction, Equilibrium would say, so reaction shifts right to get to equilibrium. And where thermodynamics says reaction is non-spontaneous in forward direction, equilibrium would say reaction shifts left to get to equilibrium. So there are really two ways of looking at the same thing. We talk about and we calculate equilibrium constants when we can measure concentrations or partial pressures. We talk about thermodynamics when we can measure delta H, delta S, and delta G of reactions, but really it's all equilibrium. Any questions about that? All